Assalamualaikum and a very good day to Dr. Amzari. Today, we from Team 13 will present the given topic on assignment 2, which is the partial differential equation. Our team consists of three members, myself, Zainul Ariffin bin Mohamad Idris with metric number 208428, Farhan Faizeen bin Rozaimi with metric number 206481, and Eugene Raphael Ghani Anak Jacob with metric number 208563. Okay. So for introduction, a partial differential equation, PDE, is basically a mathematical equation in which a function and its partial derivative are both involved. Based on what we have learned in Engineering Mathematics 1 during first semester, the derivative of a function with one variable can be represented mathematically by the following expression in figure A. A partial derivative expresses the rate of change of a function containing more than one variable. For example, the partial derivative of function f with variable xt with respect to x can be expressed in a similar method with one variable function, such as in figure B here. Similarly, the derivative of a function f with variable xt with respect to t will be represented as in figure C. Partial differential equations are usually applied on mathematical formulation and used to construct the solution for many problems that arise from physics, which require more than one variable, such as the heat transfer, water flow, and the propagation of wave. In this presentation, we will focus more on the principle and application of partial differential equation in the development of the equation from physics, specifically wave equation, heat equation, and Laplace equation.
Bismillahirrahmanirrahim. My name is Farhan Faizeen Azim. My metric number is 206481. So the objective of this report is to get through understanding of how differential equations work and to apply the differential equation in real life problems, then to have a better knowledge of how differential equations function in various applications such as heat, wave, and Laplace problem.
All right. So for the discussion of the wave equation, I would like to discuss about how we can use the partial derivative to prove the wave equation, which is based on displacement of harmonic wave, is equivalent to the wave equation, which is based on Newton's second law. So as you guys can see in this slide, based on mathematical modeling of the small amplitude transverse vibration of a string that we have done in the report, we can present the wave equation in one dimension based on the Newton's second law as you guys can see here, the double integration of function y with respect to x is equal to 1 over v squared times double integration of y with respect to t, where a 1 over v is equal to the square root t over rho. Okay, so the simplest wave in one-dimensional cosine wave with an amplitude y described by the equation y with variable xt is equal to a cos to the bracket of a variable kx minus omega t, where a is the maximum amplitude of the wave and x is the space coordinate, k is the wave number, and omega is the angular frequency. So overall, the standard wave equation in one dimension can be represented as equation 1 and equation 2. And by using the fundamentals and application of partial derivative, we can prove equation 2 is a wave equation in one dimension. In order to do that, we need to plug in equation 2 in equation 1. If the left side is equal to the right side, then we are indeed dealing with the wave equation, which is mean both equation 1 and equation 2 is the wave equation. Okay, so for the first step, we need to define the second order differentiation of a function y with variable xt with respect to x. So the first derivative, we will get a negative ka sin to the bracket of a variable lx minus omega t, while the double integration, we will get a negative k squared times y. For step 2, we need to define the second order differentiation of a function y with variable xt with respect to t. So the first derivative, we will get we will get a omega sin to the bracket of kx minus omega t, while for the double integration, we will get negative omega squared times y. Okay, so for step we need to substitute the double integration of y with respect to x and double integration of y with respect to t into equation 1, which we will get k squared is equal to 1 over v squared times omega squared. And we have to note that the wave number, which is k, can be represented as 2 pi over lambda, angular frequency is equal to 2 pi time f, and wave velocity is equal to lambda f. And by substitute those product in the equation, we will get 1 over lambda squared is equal to 1 over lambda squared. Thus, by using the standard wave equation, which is equation 1, we can prove that the form of the traveling wave on the string, which is equation 2, is also the proper wave equation since the left side is equal to the right sides. All right, that's all from me.
Heat equation. Heat equation may be a partial differential equation that is a form of U minus K delta U equal to F. So when F is equal to 0, it is a homogeneous equation, while when F is not equal to 0, it is an inhomogeneous equation. So L is said to be a linear if for any given real valued functions U and V, including the scalars A and B, follow the equation below. So if L is a linear operator, the equation is considered linear. Fx is a function of the independent variables, and the equation is called a homogeneous linear equation if f equal to 0, and it known as a inhomogeneous if f is more than if f is not equal to 0. Okay, if the partial differential equation is linear, any linear combination of solutions to a homogeneous problem is a solution to it, and all inhomogeneous problem solutions may be described as linear combinations of a specific inhomogeneous problem solution and certain homogeneous problem solutions. HT denotes the total quantity of heat in D. So let C represent the specific heat of the object and be the density of the substance P. The total heat in D is thus as the equation below. By taking the derivative, we could find the rate of heat as below. As we know, heat flows from hot to cold areas at a rate K more than 0, proportional to the temperature gradient as per Fourier's law. We also know that heat escaped from D through the boundary, resulting in the equation below, where delta D is the boundary of D and delta D is the surface measure over D. Then the integrands must be the same since the domain D is arbitrary. And as Cp and K are constant, we have derived the general form of the heat equation, that is Ut equal to K delta U. So the rate of heat in D is the total of rate of heat leaving D and the rate of heat contributed by the heat source, if there is one. So the equation, this equation where F specifies the heat source rates, you may obtain the inhomogeneous form of the heat equation from Ut equal to K delta U plus 4, plus F. So this is how the heat equation derives. Thus, we can solve heat problems using differential equation if it requires change in time.
Hello everyone, my name is Eugene Raphael Ghani and I take up my metric number is 208563 and I will be presenting the Laplace equation. So Laplace equation is the partial differential equation named after Pierre-Simon de Marquis de Laplace. Laplace equation can be used to formulate the general class of problem associated such as gravitational theory, electrostatic, dielectric, and magnetostatic in mathematical physics. All applications that culminate the development of Laplace equation have this ability to express fundamental vector field of their interest to the area as an underlying thing. So for the principle of the Laplace, the equation is nambla to the power of 2 u equal to u double x plus u double y plus u double z equal to 0. So here x, y, z are Cartesian coordinate in space, which is u double x equal to partial differential to the power of 2u divided by partial differential of x to the power of 2, etc. So the expression of number to the power of 2u is called the Laplacian of u. The theory of the solution of previous equation is called the potential theory. Solution of a previous equation that have continuous second partial derivative are known as harmonic function. Gravitational, electrostatic, steady state heat flow, and fluid flow are all examples of Laplace equation. The gravitational potential u xyz at a point xyz is resulting from a single mass locating at the point xyz is u xyz is equal to c divided by r equal to c divided by power root of x minus x to the power of 2 plus y minus y to the power of 2 z minus z to the power of 2 and u satisfied. Similarly, if a mass distributed in a region T in space with a density of P xyz, its potential at a point xyz not occupied by mass is u xyz equal to k triple derivative of P xyz divided by r dx dy dz. We satisfy the number to power of 2 once divided by r equal to 0 and P is not function of xyz. Boundary value problem in region T in space with a boundary surface S are example of practical problem involving the Laplacian equation. This issue can be classified into three categories. If U is specified on S, this is known as a first boundary value problem or the Dirichlet problem. Second boundary value problem or Newman problem if the normal derivative Un is equal to partial derivative U divided by partial derivative N is prescribed on S. Third or mixed boundary value problem or Robin problem. If U is prescribed on a portion of S and UN on the remaining portion of S. When solving a boundary value problem, we must first choose the appropriate coordinate for the boundary surface S to have a simple representation. So for the application of Laplacian equation, so the example is a question in cylindrical coordinate. So the first step in solving a boundary value problem is generate the introduction of coordinate in which the boundary surface S has a simple representation. Cylindrical symmetry, a cylinder as a region T for cylindrical coordinate. R theta z related to xyz by x equal to r cos theta, y equal to r sin theta, z equal to z. So this is a two coordinate, which is the first is cylindrical coordinate and the second is a spherical coordinate. For this, we get number to the power of 2 immediately by adding u double z to the previous equation. Thus, we get this equation. So that's all from me. Thank you.
In conclusion, partial differential equations play a very important role in modern science and also can be described as the most fundamental description of many physical processes. The science behind PDE is incredible, which can simulate real occurrences with such precision. More often than not, application come as a direct consequence. To be able to apply the differential equations to construct the mathematical modeling for a particular problem, we need to have a very good knowledge in this subject. We hope this presentation will help to build an understanding on how to apply the principle of the partial derivative to construct mathematical models for many problems in our daily life. That's all from us. Thank you.